somewhere we get the advantage of that. So whenever any object which is rolling is in contact with the surface, we consider that area which is in contact as a point. So the rolling friction is much better than sliding friction. That's why if you look at the large suitcases, briefcases, they all have tires provided. Why are there tires over there? Because they reduce the friction. Area in contact is less. So rolling friction is better than sliding friction. Now in rolling also, what is important here is my pulling the rolling friction, pulling the, like take an example, pulling a bag is better or it's pushing a bag is better. We will find out that and will come up to the conclusion that is pulling better or it's pushing better. So what are we doing it? Let's say that I have a roller here and so what we can do is that we can draw two wheels here. And from these two wheels, we'll find out that is rolling better. Sorry, I mean to say it's pushing better or it's pulling better. Okay. So let's say that the motion is something like this. And from the center, the force is applied over here. In this case, I'm pulling because the force is applied this way, it's moving like this. So it's moving in the direction of the force applied here. So there will be some frictional force acting in this direction. Let's say it's at rest. So static force is this direction. And we have weight acting downward direction. We have a normal reaction force acting in the upward direction. So let's say that this normal reaction force is R. And it makes an angle, let's say it's alpha over here. So alpha is the angle made by the force which is applied with the normal reaction force. Then if this is F and this is angle, my adjacent side will be F cos alpha. And this will be my F sin alpha. So we have F cos alpha, F sin alpha. Irrespective of what we need is mg, the weight acting in the downward direction. So I get the angle, I get the component, I get R. R plus F cos alpha will balance with mg. My vertical force will get balanced over here. So how do I get? If I take this as R1, my R1 and F cos alpha, they both will combine together to give mg, the resultant force. So what equation we will get from here? This is actually, you should draw free body diagram for this also. But I have drawn the diagram. In the exam, you will draw a diagram and you will draw a free body diagram somewhere here showing all these components. So the R1 here plus F cos alpha will be equal to mg. At any point, these two forces will be balancing each other. So therefore, what will be the value of R1? What value of R1 we will get here? It's mg minus F cos alpha. So I get R1 over here. Now we already know the relation between the R and Fs or Fk. Now what is the relation that we know? We know that Fs is equals to mu s, and let's say this is R1. So therefore Fs equals to mu s, R1 is mg minus F cos alpha. This is the equation we get. That means my static force of friction is mu s mg minus F cos alpha. This is the resultant. This is the frictional force of friction acting between, and surface. Similarly, we will find Fs now for this, and we call that as Fs dash. So now at this center we are, so I apply the force in the inward direction. So when I apply the force in the inward direction, how are the components we are getting it? Either you apply the force in the inward direction this way, or if you don't want to get confused, then you can take directly from here. This is my force which is acting in the downward, like pushing. So when we push, it's going this way. Force in this way, it's moving in this particular direction, that is in anti-clockwise direction. We'll again find the component here. Now what are the components we'll be getting? We know that this is mg. Let's say that this is my resultant, which is R2. My resultant is mg. Now we take the angle for F with respect to R2. Let's say I take again the same angle, and if I take the angle as alpha over here, what are the components we will be getting it? So let's say that this angle is again my alpha. Since it's acting in the downward direction, this is the force. My adjacent force here, that is this angle, this force will be my F cos alpha. This F cos alpha is acting in the downward direction. So my R2 is acting upward direction. F cos alpha and mg, they both are acting in the downward direction because my force is this way. So the components will be this way. So I get the component here also in the inward direction.
Oh, you're muted.
So you muted yourself.
I'm sorry. I'll explain again. See, basically what we are doing here is we are doing the rollers concept, and the roller concept is with respect to pulling and pushing. So let's say that we have a roller, and on this roller we apply a force in the outward direction. This force which is acting in the outward direction will rotate this clockwise, and it is pulling. I take the same roller and I apply the force in the inward direction, it's pushing. So our main concept is, for this particular roller, will my pulling will be more benefited or will pushing will be more benefited? This is what actually you have to learn. So I have drawn the diagram. I'll just explain you again the component. I'm pulling it ahead. So this is my force which is acting with respect to angle alpha. Now, if I find the component, I get F cos alpha component here, and I get F sin alpha. So here, let's say resultant force is R1. My R1 plus F cos alpha, they get added, and these two forces will be equal to mg. So R1 plus F cos alpha equals to mg. I find R1, which is mg minus F cos alpha. We also know Fs equals to mu s R1. I take R1 from here and I substitute. I get the Fs value, that is the force of static friction when it's pulled. Same thing we do it for pushing. I apply the force in the inward direction. When I apply the force in the inward direction with angle alpha, I get the resultant force, that the components resolved will be also in the inward direction. Since this is the force acting in inward direction, my next adjacent side will be F cos alpha, and the 90 degree will be F sin alpha. So if I find the resultant forces over here, I get this R2 inward direction. R2 will be equal to F cos alpha downward direction, mg direction. F cos alpha and mg downward direction, this is the value you get. So R equals to F cos alpha plus mg. I apply the same, and it is S equals to S R2. So for Fs I get S, mu S, R2 value is F cos alpha plus mg. So I get Fs, actually let us say this is Fs dash. So Fs dash equals to mu s, and here Fs dash is this. So Fs dash, that is the static force of friction pushing, this is the value, and static force of friction Fs when pulling is this. If you look at these two equations, that is Fs and Fs dash, what do we come to know? In Fs, my weight is getting reduced by the component F cos alpha. So my static force of friction will be less. Whereas my F cos alpha is added with it. So therefore the whole component here for Fs dash will be more. So pushing, static force of friction increases. That's why pulling, in which the component is getting reduced, my Fs will be less than Fs dash. So my conclusion will, since Fs is less than Fs dash, pulling is easier than pushing. In exam, they can ask this question: what's easier, is it or pushing? Write the